Hello everybody, welcome to today's lecture on combustion reactions. As I had mentioned in the last class, there are certain specific reactions which are of interest for chemical engineers and biochemical engineers. Combustion reaction is a very common reaction seen in most of the chemical industries and in many biochemical industries also. So, it is important for us to understand what these reactions are and what are the terminologies associated with such combustion reactions. So, in this lecture we will go through some of these concepts and try to solve some example problems which help us understand these terminologies better. What is combustion? Combustion is a process when some substance reacts with oxygen to form combustive gases which are basically the product gases, namely carbon dioxide, carbon monoxide, water vapor and sulfur dioxide, etc. So, the products which are formed here, which are carbon dioxide, carbon monoxide and all, are usually cheaper than the reactants. This is because the reactants which are taking part in the reaction are usually fuels and the fuels are very expensive. So, why is this important then? This is because the fuels which are burnt release energy. This energy which is released is used for different processes in many of the industries. Some common examples would be where coal or heating oil or natural gas is burnt to generate electricity, engines where combustion of petrol or diesel is happening so that it can be converted to kinetic energy. So, these are certain processes where combustion reactions are of critical importance. In addition to fuel, combustion can happen only in the presence of oxygen. Air is used as the common source for oxygen. Purified oxygen is usually more expensive. For this reason, a cheaper alternative, which is air, is used in most chemical and biochemical processes for combustion of fuels. So, for ease of calculations, air is considered to be 79% nitrogen and 21% oxygen. So, the molecular weight of this particular composition of air would be 28.84 grams per mole to be accurate, or 29 grams per mole roughly. So, nitrogen which is present in this air is treated to be an inert component during the combustion reactions. In reality, some amount of this nitrogen can actually get converted to NOx gases which are pollutants. These are usually in very small quantities. Because of this, they are considered to be negligible and are usually ignored while we perform these calculations. So, this particular process has specific terminologies which are associated with combustion processes. For this reason, it is important for us to learn and remember what these terminologies are and apply them appropriately. So, here are some of the terminologies which are commonly used in combustion reactions. Flue or stack gas. So, flue or stack gas is the combination of all the gases that are resulting from the combustion. This includes the water vapor which is formed. It is also called as the wet basis, based on which calculations can be performed. You also have another terminology which is Orsat analysis or dry basis. Here all the combustion gases are taken into account except for water vapor. You have complete combustion, which represents that all the carbon is converted to carbon dioxide, sulfur is converted to SO2 and hydrogen is converted to water vapor. Only when this reaction goes to completion, these particular product gases are formed. So, you have partial combustion where some of the carbon can be left as carbon monoxide instead of being converted to carbon dioxide. Another terminology which is commonly used in combustion reactions is theoretical air or oxygen. Theoretical air or oxygen is the minimum amount of air or oxygen which is required for the complete combustion to occur, which means all of carbon should be converted to carbon dioxide, sulfur to be converted to sulfur dioxide and hydrogen to be converted to water vapor. You have something called excess air, which is basically the air that is provided in excess to what is required for complete combustion. In general, fuel is a lot more expensive than air. So, this would mean supplying air in excess would ensure that the fuel, which is the limiting reactant, is fully consumed. So, thereby utilizing the most out of the fuel. For this reason, air is almost always supplied in excess. So, excess air is actually calculated based on how much fuel can be burnt, basically how much fuel is available for the combustion reaction, rather than how much fuel is actually burnt during the combustion reaction that is being studied. These two terms, theoretical air or oxygen and excess air, are actually calculated based on the assumption that complete combustion happens. This means even if carbon monoxide and carbon dioxide are both formed in a reaction, in reality, however, we should calculate these theoretical terms of theoretical air and excess air based on reactions happening in a way that all of carbon is converted to carbon dioxide, which is what complete combustion is. So, we also mentioned wet and dry basis when we looked at this. What do we mean by this? Wet basis is basically composition of a gas which is leaving the system, which includes water vapor. So, usually mole fractions or mole percentages are given. So, the total number of moles includes the number of moles of water vapor which is leaving the system. You also have dry basis, in which the compositions are given as mole fractions or mole percentages, where the same gas is accounted for. However, the total mass total moles does not account for the moles of water vapor. Here is an example just to illustrate this. If you have a gas which contains 33.33% nitrogen, 33.33% oxygen and 33.34% water vapor, then this is called as the wet basis. So, it can also be written as 50% nitrogen and 50% oxygen based on dry basis. This is because if we were to assume 100 moles of the total gas, you would have had 33.33% nitrogen, 33.33 moles nitrogen and 33.33 moles of oxygen and 33.34 moles of water vapor. So, when we calculate dry basis, we ignore the 33.34 moles of water vapor and we perform the composition calculations only based on the amount of nitrogen and oxygen, which would be 33.33 moles each. This would result in 33.33 divided by 66.66 for both nitrogen and oxygen, giving you mole fractions of 0.5 or mole percentages of 50%, which is what is the dry basis. ORSAT analysis is a traditional technique which is used for analyzing flue gases. So, this technique will only give you dry basis. So, what happens here is a fixed volume of a sample gas is passed through specific solutions which can absorb certain gases. So, when this goes through these chambers, the particular gas is absorbed by the solution, and after complete absorption the difference in the volume is measured to actually identify the concentration of the particular gas in the product gas which is leaving the system. So, caustic potash is used for absorbing carbon dioxide, a mix of pyrogallic acid and caustic potash and water is used for absorbing oxygen, and a solution of cuprous chloride is used for absorbing carbon monoxide. So, by this method we can actually use ORSAT analysis to actually get the dry basis compositions of the different flue gas which is leaving the system. Now that we have understood and learned the terminologies, let us perform certain example problems to ensure that we have fully understood and we have the grasp for performing calculations related to combustion reactions. Here is the first example problem. The composition of a gas on wet basis is given as 60% nitrogen, 15% carbon dioxide, 10% oxygen and the rest is water vapor. You are asked to calculate the molar composition of the gas on a dry basis. How would we go about performing this calculation? The first thing we need to do is we need to calculate the number of moles of each of the component, so that we can actually ignore the number of moles of water to get the dry basis. So, for this we will assume a basis for the composition which has been given to us. Let us assume 100 moles of gas, wet gas is present. So, that would be basis would be given as 100 moles of wet gas. So, this implies you have 60 moles of nitrogen, 15 moles of carbon dioxide and 10 moles of oxygen and the rest is water. So, this adds up to 85 moles, not accounting for water. So, based on the information given, we know that 15 moles of water vapor is also present. So, when we calculate the wet basis, what we would have done is we would have accounted for this 15 moles also and had a total moles of 100, which was the basis assumed, and from there we would have calculated the percentages. So, now to calculate the dry basis, we would not include the number of moles of water vapor present in the mixture. So, the total number of moles which will be used for calculations would be 85 moles. So, using this we can calculate the dry basis compositions as, for nitrogen it would be 60 divided by 85, which is 0.706 moles per mole, and you have carbon dioxide as 15 divided by 85, which is equal to 0.176 moles per mole, and oxygen would be 10 by 85, giving you 0.118 moles per mole. So, the values you have calculated here would be the dry basis, because you have ignored the number of moles of water vapor which is present in the gas to perform calculations for the composition. So, here is the second example. RSAT analysis yields 65% nitrogen, 14% carbon dioxide, 11% carbon monoxide and 10% oxygen. Humidity measurement shows that mole fraction of water vapor is 0.0700. You are asked to calculate the molar composition in wet basis. So, the information you get from RSAT analysis would be the dry basis. RSAT analysis is a technique for measuring the composition of flue gas based on absorption of gases, and this can be done for gases other than water vapor. So, the value you get for the compositions are on dry basis. You have also been given how much water is present in the form of water vapor based on the humidity data. So, that tells you the amount of water which is present, and your dry basis will give you the information of the other components. Now that we have all this, we have been asked to calculate how much of each of these is present in terms of wet basis. So, let us go about and try to do this calculation. For performing these calculations, let us assume a basis of 100 moles of dry air entering into the system. So, basis would be 100 moles of dry air. So, based on the humidity data, we know that mole fraction of water is equal to 0.0700 moles of water per mole of wet air. So, this can be converted to moles of water per moles of dry air. So, because only then we will be able to use the values for the basis easily. So, we have the information for amount of water, which means the amount of the fraction of the other components in the wet air would be 0.930 moles of dry air per mole of wet air. So, using this we can calculate the mole fraction of water per, using this we can calculate the mole ratio of water to dry air. So, which would be 0.0700 divided by 0.930, giving you a value of 0.0753 moles of water per mole of dry air. Now that we know the amount of water present per mole of dry air, we can calculate the number of moles of water present for 100 moles of dry air, which is the basis used. So, 100 moles of dry air would contain 0.0753 times 100 moles of water, which is 7.53 moles of water. So, based on the RSAT analysis, we know that the 100 moles of dry air actually is constituted by 65 moles of nitrogen, 14 moles of carbon dioxide, 11 moles of carbon monoxide and 10 moles of oxygen. So, now in addition to this we have 7.53 moles of water vapor. So, for performing wet basis we need to calculate the total number of moles of this mixture including water vapor. So, which adds up to 107.53 moles. So, the wet basis calculations for each of these components would be as follows. You have nitrogen which would be 65 divided by 107.53, carbon dioxide would be 14 divided by 107.53 and carbon monoxide would be 11 divided by 107.53, oxygen would be 10 divided by 107.53 and water vapor would be 7.53 divided by 107.53. These fractions represent the mole fractions of each of the component on wet basis. So, by performing these calculations we have converted dry basis into wet basis. Moving on to the next problem. Here is another example where you are asked to calculate percent excess of air. As I mentioned, air is usually supplied in excess and here you have been asked to calculate how much excess is the air which is being supplied. 100 moles of butane and 5000 moles per hour of air are fed into a combustion reactor. You are asked to calculate the percentage excess of air. So, before we do that we need to understand the stoichiometry for this reaction. Butane would be C4H10. This reacts with oxygen to form carbon dioxide and water vapor. So, we will assume complete combustion, which means only carbon dioxide and water vapor are formed. You do not have carbon monoxide which is being formed. So, this is not a balanced equation. We now need to balance this equation. So, we have 4 atoms of carbon taking part in the reaction. So, we need to have at least 4 atoms of carbon which is being produced. So, now carbon is balanced. If we were to balance hydrogen, we would have to add a 5 as a stoichiometric coefficient for water. So, thereby 10 atoms of hydrogen coming in and 10 atoms of hydrogen leaving. So, oxygen now needs to be balanced. Here we have 8 plus 5, 13 atoms of oxygen leaving the reaction. So, this means you would have 13 by 2 or 6.5 moles of oxygen, 6.5 molecules of oxygen entering into the reaction. So, this is the balanced equation. So, this means theoretically how much oxygen is required. Theoretical oxygen requirement would be 6.5 moles of oxygen per mole of butane. So, here you have 100 moles per hour of butane being supplied. So, which means 100 moles per hour of butane would require 650 moles of oxygen. In this case you have 5000 moles of air which is supplied per hour. So, what does 650 moles of oxygen represent? So, this would contain, air would contain oxygen and nitrogen. We will assume a composition of 79% nitrogen and 21% oxygen. So, the theoretical requirement of oxygen is 650 moles per hour of oxygen. So, based on this theoretical requirement for oxygen, we now need to calculate the theoretical requirement of air. Air contains oxygen and nitrogen. For simplicity we will use 79% nitrogen and 21% oxygen. So, this 650 moles of oxygen would be present in how many moles of air? That would be the theoretical requirement for air. So, the theoretical air requirement for 100 moles per hour of butane would be equal to 650 divided by 0.21. So, this gives you a value of 3094 moles of air per hour. Now that we know the theoretical requirement of air, we need to calculate the percentage excess of air. So, percentage excess of air can be calculated as follows. Percentage excess of air would be equal to air fed minus air required for theoretical complete combustion divided by air required times 100. So, this would mean 5000 moles which is actually fed per hour minus 3094 moles which is required per hour divided by 3094 moles that is required times 100, giving you a percentage excess of 61.6%. So, with this we would have calculated the percentage excess air that is being supplied to the system. With that, we have come to the conclusion of the introduction for combustion and combustion reactions. So, this introductory lecture gave us some information about the different terminologies and some fundamental calculations which are associated with material balances that would be done for combustion reactions. Now that we have this understanding, in the next lecture we will look at performing material balance calculations for combustion reactions. Thank you.